Hi, everybody. How are you?
Hello, doing well.
Okay. My computer's running slow. Hang on, I gotta. It looks like people are in. Okay, I'm just gonna put this off to the side here. Okay, so some history stuff before we start. Give me a sec. There. So we're going to start chapter 3 today. This is 3.2. We're probably going to roll into 3.2. 3.2 is not too big. And then we'll finish up 3.3 tomorrow and 3.4. And then hopefully we'll have time on Thursday to kind of some new questions, right? We'll see. I'm sort of loath to start. I don't want to start 3.5. I think I'm going to make that not exam. We'll see. In the past I did, but in the past I didn't have 2.6 on, so most likely chapter 3.5 won't be on the exam, just so that way we can have like Thursday, the class period, to answer questions. If you guys notice on the Blackboard page, I put up some stuff yesterday. I sent out about it. So we have, there's a folder on our main course material page that says, I think something like review for exam 1. This is going to help you. There's like some old review pages now. Those review sheets were for when the exams, like there were only like 1 or 2 exams in a semester, so there's like a lot of stuff in there. I just said basically which questions to take a look at. So don't worry if you're looking at it and some of it looks like completely unknown. Some of it we're going to cover today and tomorrow, and then some of it we're going to get to later in the semester. Okay, so don't sweat when you're looking at it right now. Anyway, so that should be up there. Also, I put a copy of the quiz, the solutions to the quiz, so you can get a feeling for it. Also, there's the solution for the extra credit part on the quiz, which is a geometric series. You want to be able to see the nuances on that, how you're going to work through that. Let's see what else. Yeah, lecture notes, lecture videos are all still being posted up online. I think that's it for administrative stuff. So I guess without much ado, we're going to plow right ahead into chapter 3. Don't forget, by the way, before I finish, don't forget that this Thursday, your homework set is due again. So this is 2.6, 3.2, 3.3, and 3.4 will be due on Thursday at midnight, by midnight. You can pass it in anytime, but I'll start, taking a look at it probably on Friday. And then we'll set up a 24-hour window again for our exam. Unlike the quiz, where you had a smaller time frame to take the quiz, the exam will be the whole length of time for the class plus 15 minutes to upload stuff. Okay, so just some administrative things. All right, so let's go ahead and get started thinking about chapter 3. Chapter 3 is very exciting. Let's see, here we go. Make sure this is in focus here. Okay. All right, so we're going to do chapter 3.2. Okay, so chapter 3.2 specifically is called the Binomial and Hypergeometric Probabilities. But chapter 3 itself is about random variables. That's like the title for chapter 3, but then chapter 3.2, give me just a second. Chapter 3.2 specifically is about binomial and hypergeometric. And these are probabilities. We're actually going to learn today, these are probability distributions, probability distribution functions. they're going to form the basis for the underlying basis for a statistical analysis when we move on to the second half of the class, second half of the semester, where we basically, the first half, talk about probability distributions, how do we think about probabilities, and then we build on that in the second half of the class to use that as the underlying makeup of our statistical analysis. Okay, a lot of stuff that we do, though, is based on binomial probabilities, so we're going to spend some time talking about that today. So let's just talk about, I want to put up some definitions because we need to be able to have a common understanding about what things are when we talk about them. So the first thing is, let's just define what's a random variable. Okay, so a random variable, oh, give me just a second. There. So a random variable is, it's essentially, it's a function, even though we call it a variable, but it's a larger kind of like a meta-analysis. It's a function that associates, oops. Let me write this down, and then we'll talk about it. Okay, so a random variable in itself is it's essentially, it's a function, right? We call it a variable, but it's a way of kind of taking a look at, we've got all this, sample space, right? We've got certain subsets of these sample outcomes, and we're going to describe certain subsets of those sample outcomes as a part of a random variable. We want the subset of heads on a coin toss, or we want the subset of tails on a coin toss. Then I want to take those random variables that are assigned to heads and tails, and I want to do things with them, right? I'm going to actually manipulate these random variables a little bit more. They become a way for us to describe the data, and they become a way for us to describe the probabilities on a much more algorithmic level, instead of just looking at this collection of data, right? Because as you'll find as you go along, when you're experimenting, you're going to be accruing lots and lots of data, and you need to have some way to analyze it. Okay, so a random variable is a way to kind of think about that. It's a variable, but it's also a function. And when we say it's something that we define to be important, that's like, you remember when we were talking about events, right? This is event A. The number of people who, do something in this particular sample set. So we need to be able to define, because we think that's important. And so we're assigning that its own random variable, okay, just like we did with events. So within random variables, I can have two different types. Okay, one is continuous and one is discrete. Okay, we're going to spend time on each one of those. So let's just talk about continuous. So our continuous random variable, this will get its own chapter. Today we're going to talk about discrete random variables. So the continuous random variable is if the outcome, oops, the outcome that we can get out of whatever we're defining our random number to be, our random variable to be, is any real number within our given interval, okay? A real number, right? So if I say if it's between 0 and 1, it's going to encompass all those possibilities, all the decimal parts within there, okay? It's all a continuous variable value, set of values within that interval that we're looking at. If we talk about a discrete random variable, okay, now something like that's discrete is only going to have a specific set of values, okay? So I have a value here, and then nothing, and a value here, and then nothing, and a value here. So it's a discrete set. It's a very, let's write down, let me write down the definition and we'll talk about it. So it's a finite number of possible values that the random variable can have. It also can be what we call like infinitely countable, right? That it's an infinite set, but it's countable, okay? I'm getting notices on my screen, by the way, that my internet connection is a little bit unstable. If we if something disconnects or whatever, then we'll log out and we'll log back in and we'll start the class again. So bear with me if the internet kind of goes a little bit wonky here. So it's a countably infinite number of possible values that a random variable can have. Okay, so unlike a continuous, which is all the possible values, a discrete set only has very specific, you can kind of think about it as like a, I hesitate to say integer, but like integer notations between, within some interval. Or it's countably infinite, which means I can set some kind of an algorithm to describe how I'm going to get all of these particular values. Okay, so today we're going to be focusing on discrete random variables, and I think tomorrow we'll start on continuous random variables. We'll talk about them. Okay, so our different variable types. Okay, and I'm going to jump right into, this is a little bit of like background information, and I'm going to jump right into chapter 3.2. There we go. Make sure it's on the screen here. Okay, gotta make sure it's all lined up. Okay, so our binomial experiment. Okay, binomial experiments are really important. It's a binomial, meaning I've got two possible outcomes, a yes or a no, or what we also really call a success or a failure. Sometimes they're assigned numbers. A success is assigned the number 1, a failure is assigned the number 0. We're going to sum up all of these successes, right, and get some kind of a value, right? But let's just take a step back and talk about what's a binomial experiment. Okay, because the binomial experiment actually tends to be a really important probability distribution that gets used in the background of a lot of experiments that happen. So let's just define it first, and then we'll go into the details. So we've got, for part 1, there must be a fixed number, that's an M number, of trials. That's our first priority. Question of part 2, property 2 is each trial must have only 2 outcomes. This is our success or failure, okay? This is our, we'll call it success, failure, or what we've also been calling a yes or no so far, okay? Part 3, the outcomes of each trial, this is important, each trial are independent of each other, okay? And that's an important thing. So when you're running experiments, when you move on in your careers, when you run experiments, you want to make sure that you're controlling for the fact that each person that you're bringing in to do an experiment on, whether it's just a survey or you're testing their hearing or whatever, that each person is an independent trial, okay? So that that the results aren't being influenced by what's come before. So we make the assumption that things are independent unless we look at the data and we think, hey, things look a little funny. Maybe they're not independent, but otherwise we assume that everything is. And we try to design the experiment so that they are independent. Okay, so now the probability, the last one, probability of success must remain the same for each trial. Okay, this kind of goes hand in hand with each trial being independent with one another, right? We don't want the probabilities changing as we go along. That would defeat the whole purpose of things being independent. Okay, so so the outcomes of our binomial experiment form the basis, they form the data for what we call our probability, our binomial distribution. The binomial distribution is pretty important. It gets used as the basis for a lot of probability distribution functions. Okay, so I just want to also mention in terms of notation, you'll also see this in your book, and you may actually read it or hear about it elsewhere. So we consider this a binomial experiment, right? The outcomes of which are going to form our binomial distribution. The binomial experiment can also be called a Bernoulli experiment or a Bernoulli trial. Bernoulli was I think he was Swiss, maybe a mathematician a couple hundred years ago who studied this, right, and then who kind of quantified this as an idea. It's now mostly called the binomial experiment. If you say Bernoulli, you know, sort of out in general, people may not understand what you're talking about unless they're coming from a statistical background. But a binomial experiment, you know, a lot of people understand, they've heard of that before. But just so you know, I think our book uses Bernoulli and binomial somewhat interchangeably. Okay, but Bernoulli is essentially a binomial experiment. Okay, so let's talk about notation for our binomial. We're laying the groundwork for a lot of stuff because we're going to be using this a lot. Okay, so our notation goes something like this. We've got a capital P. P of S is our probability of success. Okay, and likewise, I'm going to say P of F is our probability of failure. These are related, obviously. It's a binomial, so if I'm given one, I can calculate the other. We'll do stuff like that today. And now, so I've got my probability of success. My actual lowercase p is the actual numerical value for our probability of success. Okay, p is what we use actually in our equations, the lowercase p. And then q, okay, our lowercase q is 1 minus p. This is our numerical value for the probability of failure. Okay. Can you guys see that? Okay. All right. So, you know, in reality, we're looking at probability of success equals lowercase p, probability of failure equals 1 minus p, which is our q. You can use 1 minus p or you can use q. We use them interchangeably in our notations. In the notes that we're going to talk about, in the examples we're going to do, in the homework, you can see it, the same thing. So also one of the things that's important when we do this is we need to know what's the number of trials. Right? How many experimental trials did we go out and do? Okay. Oftentimes you want to be able to calculate, you want to know, so let's say I need to have like 100 experimental trials and I'm going to get a certain probability of success. I'm going to get a certain probability, you know, overall my whole distribution based on the outcomes of the experiment that we're doing. Sometimes you can reverse engineer it and say, how many numbers of trials do we need to do in order to get the results, you know, have a higher confidence level in the results that we're looking for. Right now, in the early chapters, chapter 3, we're going to be telling you the number of trials that we're doing. As we move along in the statistics part, we're going to do some examples where we solve for the number of trials so that we kind of, we know like how strong our experiment is essentially. Okay, X is our specific, this is like our random variable, the number of successes in N trials. Okay, so I would say I would write it like this, right? I've got, you know, I start at 0 and I go all the way up to the number of trials we have, okay? And then X, my big X, is the number of successes that we've had within that, okay? I'm going to sum up. This is like where we say our success is equal to 1, our failure is equal to 0. So I'm just going to add up all the successes that I've had. Okay, but X can be 0, 1, 2, 3, and so on and so forth until we hit N. Okay, there's no limit. We try not to predispose ourselves in terms of what we expect. All right. So this is our notation for our binomial distribution, okay? I'll give you guys a second to finish writing it. And then we're going to take this notation, okay? And we're going to put it into our probability, basically our binomial probability. Okay? Okay, so our binomial probability, let's go ahead and write it out. So we've got this random variable. Let's start calling it random variable x. That's a capital X, okay? Random variable x, and that's comes from our binomial distribution, which is a function of n, the number of trials, and p, the probability of success. This is how we're going to start to think about it. Okay, so x is the random variable within our binomial distribution, our binomial probabilities, okay, as a function of these two variables here. So we want to look at what's the probability of getting k successes in n trials. Okay, we're going to specify what's, we've polled 100 people. We want to know, what's the probability that 50 of those 100 people are going to say yes to whatever we're polling. Okay, so k is something that we're going to specify. That's part of what we're looking for. Okay, so what we would say is, what's our probability? We're looking for k, right? And this is a function of n and p. This is part of our notation. And it's going to look like this. This is the probability that our random variable x is equal to k. Okay, so I want my random variable to equal what I'm looking for, what I'm setting as important. And then that's going to be equal to this. And choose k, this is our binomial coefficient, times p to the k, 1 minus p to the n minus k. Right, I could have written q here. Oops. I could have written q here, but I wrote 1 minus p so that you would see very clearly. Now k can equal 0, 1, 2, so on and so forth up to n. Okay. So remember when we did n choose k yesterday, let's just write that down for reminding ourselves. Okay, in terms of our factorial notation. Give me a second. There. Okay. Okay, so let's try an example. So I'm pulling out my example sheet for 3.2. I'm looking at example 1. We've done this one before, right? But now we're going to start thinking about it in terms of our binomial probability. We're going to start off with examples that we've seen before that we can enumerate so we can like cross-check the stuff that we've done before with what we're learning now. Okay, and then we're going to make our examples a little bit more complicated. Okay, so we've got this. A coin is tossed 3 times. Find the probability of getting exactly 2 heads. And this is pretty straightforward. A coin is a binomial experiment. I have a head or a tail, right? I have 2 options, 2 outcomes, okay? We can actually enumerate this out. We've done this like in the first week, right? Where we enumerated out all the different possibilities. I could get head, head, and a head on each toss, head, head, and a tail, head, a tail, a head, so on and so forth. So we'll do that at the end just to cross-check the our new algorithm, okay? So let's think about this one. So I'm going to start taking notes and writing down the stuff, how it relates to it being binomial. So this is binomial, right? Because we have a fixed number of trials. Right, we're only going to toss this coin 3 times, okay? For a fixed number of trials, we have only 2 outcomes, right? Which are a head or a tail. This is our binomial part, okay? 2 options. And each outcome is independent. Right? What I got on the first coin toss has no effect of what I'm going to get on the second coin toss. I'm just tossing this coin 3 times. And then the probability of success is constant. We're told, yeah, we're going to assume it's a fair coin until we're told otherwise. So the probability of success is 1/2. A 50% chance of getting a head, 50% chance of getting a tail. Okay. So given this, right, it satisfied our criteria for being a binomial experiment. So let's go ahead and think about it. So we're saying, what's the probability of getting exactly 2 heads? So I'm going to write it like this. The probability that big X, my random variable, is equal to 2. Okay, exactly 2 heads. So this is, I'm going to do 3 choose 2 because I have 3 trials. I want to get 2 heads. Okay, so 3 choose 2 tells us, all the different ways that I can get 2 heads within this combination of 3 different trials. Okay, now I've got my P, probability of success, which is 1/2. I'm going to raise that, right, to my kth power. I've got the probability of failure, which is also 1/2. I'm going to raise that to the 3 minus 2 power, which is 1. Okay, so this is going to equal to, this is 3 factorial. This is my binomial coefficient, 2 factorial over 3 minus 1 factorial, right? This is 1/2 squared times 1/2, which is really like 1/2 cubed, right? So let's do this. So 3 factorial, this is, let's write that here. So 3 times 2 times 1 all over 2 times 1 times 1 factorial. Remember, 1 factorial is just equal to 1. So this part cancels out with that part. So just get 3 times 1/2 times 1/2 times 1/2, right, which is equal to 3 all over 8. Okay, so this is the probability that I'm going to get exactly 2 heads when I toss a coin 3 times. We did this like last week, right? So let's do out from what we did last week. Let's enumerate our sample space just so we can confirm it with what we saw before. So our sample space is going to look like this. Head, 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 tails. So this is one of my options, right? Head, tails, head. So I've got 2 heads again. That's another option. Tails, head, head. There's another option. Tails, oops, tails, head, tails, head, tails, head, tails, tails, and tails, tails, tails. Let me make sure. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I have 8 total sample outcomes. Okay, we wanted to do exactly 2 heads. So I've got 2 heads, 2 heads, 2 heads. So I have 3 outcomes out of a total of 8. Okay, which is the result that we saw last week when we were enumerating our sample spaces and calculating our basic probabilities, right? Now we're looking at this a little bit more broadly, which is that this is a binomial experiment. Heads or tails is success or failure. Heads is our success. Okay, so the probability of success is 1/2. Probability of failure is also 1/2. Okay, 3 choose 2 tells us, right, the different permutations, the different ways that the heads can show up. Okay, and then this helps us figure out like our total sample space. All right, so no longer do we have to rely on enumerating out this whole sample space. I can kind of think about this more broadly in terms of an algorithm, my probability distribution. Okay, example 2. Okay, so example 2 says, we have a survey. Surveys are common examples for this because we ask people, do you feel this way, yes or no? Do you feel that way, yes or no? So a survey found that 1 out of 5 people has visited a doctor in any given month. If 10 people are selected at random, find the probability that exactly 3 will have visited a doctor last month. This is just, by the way, a common example. We'll see this in statistics where we've got, some kind of a small sample size or a small probability, a small set of data, and we're kind of using that to make general assumptions about the overall population. Okay, so that's the whole point of all this is we've got this, small survey. We want to be able to select 3 people at random, and then just kind of be able to generalize from the smaller sample size to the general population. So keep that in mind because we'll be doing that a lot in statistics. Okay, so find the probability that exactly 3 people will have visited a doctor last month. Okay, so let's start writing down the different pieces that we have and how they fit into our, it's binomial, right? Because have you visited a doctor in the last month? Yes or no. So that's your yes is our probability of success, no is our probability of failure. So we're going to do, we select 10 people at random, so our n is equal to 10, okay? We want to find out if the probability that exactly 3, so that means that our x, our random variable, is equal to 3. And so this is our probability that k equals x, or x equals k, which is equal to 3, okay? Our probability of success, right, we said 1 out of 5 people. So 1 out of 5 people went to the doctor's office. That was our probability of success, which means that our q, which is 1 minus p, is going to be the people who didn't go, which is 4 out of 5. Okay, so that's our probability of failure. You didn't go to the doctor's office. Okay, so this is binomial because I have a yes or no. And then it's each trial, each person that we're surveying is independent. And it's finite. Okay, we don't have to say it's countably infinite. We'll do a countably infinite example later. Okay, so let's put this in. So we want to know what's the probability that our random variable x is going to equal to 3. Okay, so I'm going to set that up. So I have 10 possible people. I want to choose 3 out of them. So this is going to give me all the different ways that those people can be represented. Okay, P, my probability of success, 1 out of 5, all raised to the kth power, right? My probability of failure, 4 out of 5, is 10 minus 3. Okay, so it's going to be raised to the 7th power. So let's do this out. So this is 10 factorial all over 3 factorial, 10 minus 3 factorial, times 1/5 to the 3rd times 4/5 to the 7th. Okay, I'm just going to plug these into my calculator, right? I'm going to multiply everything through, and I'm going to get this was approximately equal to 0.201, okay, as a probability, which translates into roughly 20% chance, okay, in terms of what we're on. It's a 20% chance that exactly 3 will have visited the doctor's office within the last month, based on the data that we have so far. Okay, maybe we need to broaden our surveys to get a different probability of success. You know, these are things that you will check out experimentally as you're working. Okay, give you a second to finish writing that down. Okay, okay, so example 3. What says this? Example 3 says, a survey found that 30% of teenage consumers receive spending money from part-time jobs. If 5 teenagers are selected at random, find the probability that at least 3, now watch, I put this bigger, at least 3, like on a test or quiz, I won't write this really big or in bold, but you'll have to be able to read through the problem very carefully and look for words like at least or at most or exactly equal to. These are clues for how you're going to answer the problem. So find the probability that at least 3 will have part-time jobs. Okay, so let's start thinking about what this means, right? So 5 teenagers are selected at random, okay? So that means my n is equal to 5. Let me see that there. N is equal to 5. And if we say at least 3, right, that means, let's write this down, at least 3 means I'm looking at the probability of 3 and the probability of 4 and the probability of 5 together, at least. So I could have 3, or I could have 4, or I could have 5. So 3, 4, or 5 is going to cover my at least 3, okay? So let's think about it. My probability of success comes from here. We found 30% of teenage consumers were success in terms of our binomial experiment. So 30% translates into 0.3 as a probability, which makes our Q, 1 minus P, equal to 0.7. Okay, so this gives us our P and Q. We have our total, we've got what we're choosing for, okay? But I can't just plug it in and do it like we did before. I have to think about these things individually. So I have to calculate out my probability that I have exactly 3, okay? Which means I'm going to do 5 choose 3. I've got the same probability of success raised to the 3rd power. I've got the probability of failure, 0.7, raised to the 5 minus 3, 2nd power. So this is 5 factorial, 3 factorial all over 2 factorial, 5 minus 3 factorial, times 0.3, 0.7 squared. And this gives me roughly 0.132. Okay, so this is my probability of getting 3. Now I'm going to do probability of getting 4. Okay, so I'm going to go 5 choose 4, 0.3 to the 4th power, 0.7 to the 5 minus 4. This is equal to 5 factorial, 4 factorial over 1 factorial, right? 0.3 to the 4, 0.7 to the 1. This one is approximately equal to 0.028. Okay, right? We said probability of 3, 4, and 5, so I'm going to take a look at probability of 5. I'm going to do the same thing. So I'm going to go 5 choose 5, 0.3 to the 5, 0.7 to the 5 minus 5, okay, which is going to lend us to, this is 5 factorial all over 0 factorial all over 5 factorial. Okay, this is just going to reduce down to 1, right? Remember, we defined 0 factorial as being equal to 1, 5 factorial, 5 factorial, they cancel each other out. This whole thing is equal to 1. I'll put that right here in parentheses. So this is 0.3 to the 5th power, and this is 0.7 to the 0th power. This is equal to 1, okay? So this is approximately equal to 0.002. Okay. So I calculated out the individual probabilities. Now, if I want to go the probability that x is my random variable, right, is at least 3, which is like saying x is between 3 and 5, inclusive, right? It could be 3, it could be 5, it could be also be 4. Okay, this is going to equal to the sum of these individual pieces. Okay, I'm going to put these together. 0.132, 0.028, 0.002, and I'm going to get 0.162. So I have a roughly 16% chance, right, that if I select 5 teenagers at random, we're going to get at least 3 are going to have part-time jobs, okay, given the data that we have so far. Give you guys a second to finish writing that. Okay. All right. Example 4. Just scroll down a little. Maybe I can leave a little bit up on the page there. So example 4 says, we've got this company. It has 9 computers. It uses those computers for data storage. So the probability that any one of them is not working is our probability of failure, PF, which is 0.06. So we need at least 7 working. So 7, 8, or 9 need to be working, right? I mean, at least bigger. Working for the company to operate okay. So that's the probability of success is I have 7 computers or 8 computers or 9 computers working. So what's the probability of the company working okay? It was our probability of success, essentially, right? So let's start thinking about what we need to do. So I'm going to start writing out. So the probability of failure equals 0.06. We were given that, so I'm going to take notes, which means that my probability of success is 1 minus the probability of failure. 1 minus 0.06, 0.94. This is equal to our lowercase p. Okay, this is equal to our q in our equation for when we're trying to plug things in. So we've got 9 computers, so our n is equal to 9. This is what we're taking a look at. It's binomial, right, because it's either working or it's not. Success or failure, it's working or it's not. So at least 7 is going to mean 7 or 8 or 9 need to be working in order for the company to be successful, okay? So this is also, we're going to make the assumption I'm going to write down. I'm going to assume that the devices, or computers, are independent. It's okay for you to state your assumptions, right? It wasn't in here. We didn't state it ahead of time, but we're doing a binomial experiment. We're checking to see if this company is going to be okay. I'm going to assume, unless I'm told otherwise, right, that the devices are independent, okay? If the devices are not independent, we kind of need to scrap this model. Independent, then we need to scrap the model and then come back and then think about, you know, if one computer fails, then that's going to cause a cascade reaction to everything else. But we're going to assume everything's independent, and we're going to operate that way. All right, so what I'm looking at is the probability that my random variable, x, is between 7 and 9, inclusive, because it could be 7 or 8 or 9, like we said before, okay? Which is equal to the probability of 7 plus the probability of 8 plus the probability of 9. This is a discrete random variable, so this means 7, 8, or 9. Okay, when we get into continuous, we're going to do similar things, but we're going to have a different method for being able to sum things up between here. Okay, so for right now, discrete, I can just sum it up. So like we did in the previous example, okay, I'm going to calculate out each individual probabilities, right, 7, 8, and 9, and I'm going to sum them up. So I'm going to say 927 times 0.94, that's my probability of success raised to the 7th power. My probability of failure raised to the 9 minus 7, 2 power. So this is, I'll write this down below, probability of 7. Plus, we're going to do it for 8. 9 choose 8, 0.94 raised to the 8th power, 0.06 raised to the 9 minus 8 first power. This is our probability of 8. Plus, 9 choose 9, 0.94 to the 9th power, 0.06, right? 9 minus 9 is 0. Okay, this is our probability of 9. Okay, I'm summing up each individual one. Okay, And when I do this, I get this is approximately equal to 0.986. It's a pretty good probability, which means we have a 98.6% chance of the company operating okay. Oops, let me write this up here. There. Okay. Which is good. You want it to be high. You want your company to do well. Give you guys a second to finish writing that down. Okay. I just want to mention example 5. I think, let me just check. I think, yeah, example 5. So example 5, I'm actually going to skip. It's kind of a convoluted example. I will write it into the lecture notes and I'll put it up so you guys have the solution set for it. It's kind of convoluted and it isn't really worded very well. So I'm going to skip it in lecture today to go on to other examples that are more meaningful. But I will give you guys the solutions for example 5, and I'll post them up when I scan them and you can take a look for it. Okay, but for today, for today's lecture, I'm just going to skip that example. Okay. So example 6 is about what we call hypergeometric distribution. So let's talk about what that is first before we jump into that example. Hypergeometric distribution comes when we sample things and we don't replace them, right? So remember in the beginning, like last week, we had this bucket, we had chips in the bucket, we took a chip out and we didn't replace it. So it changed the probability, right? And we, based on what we got from that chip, we were going to do different things. We set up the whole tree that told us like what the different possibilities were, okay, because we didn't replace those chips. So basically, each trial is going to be dependent on what happens before because we're not replacing anything. Okay, so in a sense, it's still a binomial distribution in the underlying data. It's still a binomial distribution. Did we get this outcome or not? Yes or no? So it's still binomial. And it's also, we can assume that each trial that we're doing is independent. I'm sorry, so in the binomial, each trial is independent. So we sample with replacement. Okay, but now with the hypergeometric, like we just said, okay, hypergeometric, the probability of success doesn't remain constant because we're not replacing things. It may be binomial in the background because do we get this chip or not, that kind of a thing, but the probability is changing. Okay, so because the probability is changing, each trial is going to be dependent on what happens before. Okay, so as the experiment's progressing, our probability is changing, right? We saw that when we were taking the chips out, the probability of getting that chip again is going to change because we're now decreasing the pool. So So the big thing about hypergeometric, how do you know to use hypergeometric? And it's because you're selecting things and you're not replacing them back. Okay, so essentially we can think about each trial as being dependent on what's happened before it. Okay, so just as an example for what we were doing before, we would say we had some kind of a bucket. And within this bucket, we've got R number of red chips, right? R is the number of red chips. W is the number of white chips. Okay, and then R plus W is big N, which is our total number of chips. This is what we use to start with. Okay, we're going to start with this number of total chips. So what happens, right, in a hypergeometric example is we are going to select lowercase n. I'm going to take out of this bucket n chips, lowercase n chips without replacement. So I'm going to take these out. Each time I go, I'm not going to put them back, right? So I'm going to take them out, and maybe I'll look at them, take it out, look at it, take it out, look at it, take it out, look at it. But I'm still taking out and chips, but I'm not replacing. Because I'm not replacing it, that's how our probability of success is changing as we go. Okay, and we've got K is what we're looking for. Okay, so K is the number of chips of a particular type that we want. Say, we'll call it red chips. Right? So we take out lowercase n number of chips out of this bucket without replacement, and I want to know, do I have K number of red chips in that pile that I've selected out? Okay, so now we can say with our hypergeometric probability, the probability that our random variable x is equal to K is going to equal to a distribution that looks like this. R choose K, W choose n minus K, right? So I'm taking out lowercase n number of chips. I want to know how many of those K are red. So whatever's left over has to be white. And now that's going to be divided by the total number of chips. And, oops, sorry, you can't see that. That's going to be divided by, it's almost like a percentage in a way, right? Where I'm looking at, it's not a percentage, but you can kind of think about it like a weight, where I've got total number of chips and I'm selecting out this many. The red is what I'm looking for. The white is what's left over, okay? And this is going to give me my overall probability, okay? We're using chips as an example, okay, but that's kind of how you want to be able to think about it. Okay, so I'm going to put a box around this because this is our hypergeometric. We do this, right, and then we do this R choose K, right, that tells us essentially all the different ways that I can choose a red chip. I can choose a red chip on the first, and then I can choose a red chip on the second, or I can choose a red chip on the third or the fourth. You get the idea, okay, so it kind of gives us those different permutations for how the red chips are going to be distributed within this set of n, small n that we're pulling out. Okay, so let's do this hypergeometric as an example. This is our example 6 that we're going to take a look at. Okay, so example 6 says, let's see, get this on screen here. A routine audit of some company we use to find evidence of improper financial activity. So we've got 470 collections of money, okay? So we're taking in, we go out, we collect money from 470 different sources, right? That's actually too large of a number to check all of them for improper activity. So what we do is, out of that 470, we'll just do a random sample, okay? So a random sample, we're gonna do 19 out of 470. 19 out of 470, it's about 4% of the total, okay? Part of what we're also asking ourselves is this 19 large enough number, or is it, too small? And some of these things, when you do this in experiments, you maybe, as an auditing company, only have the resources to do 19, which is where that number comes from. If you have more resources, you obviously want to increase the amount that you're pulling. It's going to give you a better sense of the statistical spread of the data. All right, so if the company did do illegal financial stuff 10 times out of 470, so they actually were committing illegal acts, what's the probability that 3 or more of these 10 will make it into the audit? Because 3 or more is the threshold for the auditing company to show that there was actually illegal work that was being done. So that's why we've set that level here at 3. Okay, all right. So let's start thinking about what we have. So 3 or more. So 3 or more means the probability that our random variable x is greater than or equal to 3. Well, that's a lot, right? I'd have to sum up all of these, 3 and 4 and 5 and 6 and all that. So sometimes it's better to think of, complementary events. So I'm going to say 1 minus the probability that x is less than, not including, x is less than 3. So see, notice it's greater than or equal to. So 1 minus the probability that x is less than 3. So we're talking about probability equals to 2, probability equals to 1, probability equals to 0, x equals 0. Okay, so I only have 3 things I need to think about instead of a whole bunch when I want to look at this part right here. All right, so that's going to equal to 1 minus. Now I'm going to do my hypergeometric because I'm not going to put this back. I'm going to sample it and I'm going to take a look at it, but I'm not going to put it back. I'm not going to replace it into my overall bin here. So I've got 10 that I'm looking for. The first one is 3, okay? I've got 460 out of 19, right? So this is, 10 is what we've chosen, 460 is what's left over, okay? 19 is what's here, because that's what we're choosing here. And then we have 470 total out of 19 that we've selected, right? So this is our big N, this is our little n. This is our sample set here. This is our K, okay? This is the remainder. This is our red chip, our white chip, and this is what's left over. Plus, actually, this is, I'm gonna call this a minus because I'm gonna, if I wanted to do plus, I'd have to put a bracket here and then add all those probabilities up and subtract it from the one. But I'm gonna distribute my negative to all those, so I'm gonna subtract all of these from my one. 10 choose 1, 460 out of 18, 470 out of 19, 470 choose 19, minus 10 choose 2, let's see that there, 460 out of 17, and then 470 out of 19, okay? So these, right, these are just choose, right, the factorials. I'm gonna do them all. I'm gonna also say this is like the sum. I could say this is equal to K equals 3 to 10, okay? Where I do 10 choose K, 460, 19 minus K, all over 470 over 19. This isn't too bad of a sum. It's, you know, only like 7 or 8 elements that I need to actually add together. So this is equal to the complementary event. If we're doing things by hand, I want to, you know, think about complements because I only have, you know, a smaller set usually of things I need to add up and subtract. In the real world, you would write a computer program. Okay, you can do this in Excel, you can do this in, you know, MATLAB, whatever, or you can probably program your calculator to do it, where you're just going to sum up all of these values right here. Okay, so this is, you know, fairly trivial. We can probably even do this by hand, but we're not going to for time. Okay, so now let's go ahead and put this into 1 minus. So I did out this first part and I got 0.6592 minus the second part here, which is 0.2834, minus this third part here, 0.0518. Okay. Adding all those up, I got 0.0056, which is a pretty small number. Okay. So this is like saying approximately 0.56% of the time, the audit will find a problem. Oops, let me see that, find a problem. Problem meaning an illegal activity. So probably we need to increase the 19, maybe 4%, choosing only 19 out of 470 is too small of a percentage. So probably if we want to, if we want to increase our chances of actually finding illegal activity, we need to increase our sample size to be greater than 19.
I have a quick question.
Yeah.
How did you identify R and W?
Yeah, so you can think about, so R is what we're looking for, right? So in the original, let me go back to my hypergeometric discussion here. We just did R and W as examples because it was a fairly black and white or red and white type of a idea, right? So I've got red chips and white chips, and then so here, right? The question that's being asked is, right? I'm selecting out lowercase n number of chips. I want to know what's the probability that K of those. If I select out 10 chips, what's the probability that 3 of those are going to be red? Okay, and then that means white. I'm going to also possibly get white chips out of there too. I could have, you know, 10 minus 3 white chips, and then this is my overall combination. So on here, right, so red is kind of like what we're looking for. So in this example here that we were just doing in example 6, we said, what's the probability that 3 or more are going to make it into the audit? So we're looking for 3 or more. So this number here, 3 or more, is actually our red chip, right? So I want to know, you know, is that going to satisfy our criteria? And we say 3 or more because off stage, right? We've set 3 or more as the threshold for which we need to actually trigger a much more deeper audit. That was part of, you know, the example here. So we've said, I'm choosing 10, right? This is our lowercase n. So let's write this down. So our lowercase n was 10, right? Our K is equal to greater than or equal to 3, right? Which means it could be 3, it could be 4, it could be 5, 6, 7, 8, 9, 10, right? That's going to trigger our audit out of here, okay? So we did the complement so that we don't have to actually do this sum up, this value here. But what I'm looking for is at least 3, right, values because that's what's going to trigger my audit. So I have to be able to say, there is the possibility, like this 0.4% of the total, 19, that's our sample size. And then the company did illegal stuff 10 times. So I'm looking at, I know that they did illegal stuff 10 times, right? Of those 10 times, are those 10 times showing up within that 19 sample size that we actually chose? So you're kind of taking a step back and you're looking at, in the hypergeometric, the red is the chip that you're trying to identify. That's the one that I'm interested in, right? And then here, the stuff that I'm interested in is the illegal activity. Okay. Does that help?
Okay. Yeah, thank
Yeah. Okay, so that's hypergeometric. Okay, and we did a complementary event, but we could have, this complementary event is the same thing as summing up 3 and 4 and 5 and 6 and 7 all the way up to 10. It's just more computationally effective to do the complementary event. Okay, so if we increase our sample size to something, let's write this, let me finish writing this down. Sample size greater than 19, right? So if I choose maybe 100 out of 470, I've now increased my chances that within that 100 that I'm sampling, I'm going to get at least 3 of them that are going to show the illegal activity, because they did 10. They did 10 illegal activities within there. So we want to kind of, if we broaden the sample pool, we have a greater chance of actually capturing the bad activity. So that's hypergeometric. And that's where we sample without replacement. Okay. I'll give you guys a chance to finish writing that down. So that's 3.2. Okay. I'd like to start 3.3 today. We're not going to go all the way through. I'm only going to go part of the way through on 3.3, but it'll give us a chance to cover the rest of 3.3 tomorrow, and then also 3.4. And if we need extra time on Thursday to finish 3.4, then we'll have that as well. Okay. So that's 3.2. I'll scan in the lecture notes, the lecture examples for 3.2, and what I have so far for 3.3. I'll put those up online later today. Okay. All right, so chapter 3.3. So we're going to go into more detail on discrete random variables. Okay, we talked about our different types of random variables. We could have discrete or continuous, and we're going to spend time on each one because the methods that we use to process discrete and the methods that we use to process and describe continuous random variables are going to be different, but the overall concept is going to be similar. Okay, but we just have to have a way of handling discrete versus continuous. Okay, so remember our discrete random variable. We're going to call our discrete random variable, I'm going to call it x or y. These things are in uppercase. You'll notice on the lecture notes it's easier to tell that it's uppercase. Lecture examples, I'll try to make my lowercase numbers look more like cursive so that you can see the difference between an uppercase and a lowercase. It gets a little hard when I'm doing it by hand. So our discrete random variable, we usually denote it with x or y in our uppercase. This is a function, we said that before, but this is a function whose domain, right, these are our inputs, our domain is the sample space. Okay, so I've got some experiment that I'm running. Okay, I'm going to specify something that I think is important that I want to look at. I'm going to assign that x, capital X, my random variable. And within this whole sample space, I'm going to say, look for this type of pattern. That I only want 2 heads out of, I'm going to roll toss a coin 3 times. I only want 2 heads. Okay, so we're defining what these random variables are because somehow we think they're important to our experiment. Okay, so function, the domain of this random variable is the whole sample space because I'm pulling things out of that sample space to do stuff with it, to analyze it further. Okay, so then the values of a discrete random variable are finite, or they're countably infinite. Countably, right? Which means, they're finite in the sense, but there's an infinite stream of them. But because they're countably infinite, I can come up with an algorithm to describe this whole infinite stream, like we do with our geometric series. We're defining this this set here. Okay, so one of the things that we want to talk about when we talk about random variables is what we call a probability distribution. Probability distributions are really important, okay? Because what they're going to give us is a picture for, we've got all these different, we've got a random variable, it could take on certain values. What's the probability that it's going to take on certain values? Okay, we need to have that, or we need to be able to build it so that we can then analyze what's happening in our system. So probability distribution of a discrete random variable is, we'll just write it as the list of probabilities associated with each outcome, with each possible value, with each of its possible values. So I have a random variable that I defined. I want it to, be equal to something, right? It's gonna, the number of heads or whatever. Then I want to say the probability that this random variable could equal to 1 is this value. The probability that this random variable equals 2 is this value, and so on and so forth. I need to be able to either come up with that or be given that so I can do something with it. What we're going to do with that is what we're going to learn in this chapter and then in this class. Okay. So this probability distribution function, right, is, and for discrete random variables, the probability function for discrete random variables is called a probability mass function. We call it a mass function when it's a discrete random variable. We call it a probability density function when it's a continuous random variable. Some books just call them all probability density functions. Okay, it basically just tells you where the probabilities are assigned given the specific outcomes that we have. Well, I'll probably try to keep it consistent and say probability mass function for a discrete random variable, probability density for a continuous random variable. They're describing the same thing, but just different types of variables. Okay, all right, so let's talk about what it means to assign probabilities in discrete cases. Okay, so if I want to assign probabilities in discrete cases, so what I'm going to think about is the number of points in our sample space that it's finite, right? How many sample spaces do I have as finite or completely infinite? Okay. Okay. Our probability of S is our probability function. Okay. So how these probabilities are distributed within this sample space is going to be what we're describing here. Okay. So when we say our whole sample space, the probability of our whole sample space is still equal to 1. Then I'm going to break it apart into different sub-pieces. So all those sub-pieces have to sum up to 1. So we say our random variable, big X, it can take on a whole bunch of different values, can take on k different values. K is going to depend on what we're looking for. We'll specify k in our examples. So it can take on k different values, and then the probability that our big X is equal to a little x sub I. This is our specific value, right? So our random variable is equal to 3, or our random variable is equal to 1, say for example. And this is going to be defined as, we'll say the probability that our random variable is equal to x sub I, and that's equal to that particular probability. Okay, so my x, big X, takes on a particular value, lowercase x sub I. That probability that it's going to take on that particular value is going to have its own probability, p sub I. So that's all we're saying. We're going to break these down into individual probabilities. Okay. Also, importantly, these individual probabilities They must satisfy certain things. And it'll make sense when we write it. So each individual probabilities, they must be between 0 and 1. Okay, right, for each I, each of these pieces of I has to be between 0 and 1. It doesn't make sense if it's negative or greater than 1. And we're going to sum up all of these. Oops, piece of 2. All the way up to the total that we have. All these things are going to sum up to 1. Okay, this is actually a check that we're going to do. We've got all these different probabilities. We're going to sum them up to 1. We're going to do this in the continuous case too. Sum it all up to 1. If it doesn't sum to 1, it's not a valid probability mass function, okay, or probability density function. We get to continuous. So they must sum up to 1, and each individual value must be between 0 and 1. Okay. Make sure you have that, and then flip the page. Okay, so our probability mass or density function, whatever you want to call it.
Wait, can you go back one?
Back. I can't see who's still writing and who isn't, so definitely tell me. Do you, this part right here?
Yeah, just the 1, 2.
Okay. Let me know when you're all set.
Okay, I'm good. Thank you.
All right. Okay. So our probability mass or density function. Okay. We're going to write it like this. The probability, okay, that x or big X is equal to k, okay, which is equal to, I'm going to say the probability, I've got this, you know, smaller outcome, that's an element of my big sample space, given that x as part of that sample space is equal to k. This is all like math language. This is all just putting into math the stuff that we've just said into words. I can write this as probability that x of k is going to must equal 0 for any value of k not within our range of x. So we're defining values of x. X is going to be 1, 2, or 3. If I say what's the probability that x is going to equal 4, it's not within our range of possibilities for x, right? Which means its probability is going to be equal to 0. So just default, right? If it's not defined, it's equal to 0. We can also write this as another way of writing it, and this is more common. We see this in our book and then in the exams and stuff. We'll write the probability that x is equal to k. Okay, that's just writing it the same way. P sub x, this is a big X of k, right? That's just saying probability that x is going to equal to a particular value. Okay. Okay. All right. All right, so let's do this. I hope I've given myself enough space. So our first example, example 1, we have an unfair dice. It's 6-sided. So now the probability, and it doesn't, this is still, you know, an independent thing. So it's unfair. So the probability of getting a 1 or a 6 is higher, right? And then x, we say x is our random variable, and that's the variable of what's the face on the die. When I roll it, I get 1 or 2 or 3 or whatever. So that's the face that gets shown on the die. So the probability of x equals 1 or x equals 2 is equal to 1/4. It's an unfair die. And then the rest of them, 2, let's see, did I say 1, sorry, 1 or 6. And then the rest of them, 2, 3, 4, or 5, get to split up the other half. Okay, so 2, 3, 4, or 5 are all equal to 1/8. So I roll a die. I have a higher probability of getting a 1 or a 6 than I do a 2, 3, 4, or 5. Okay, so now the question is, what's the probability that an even number shows up after a roll of the die? Now, an even number is going to include one of our unfair rolls, and it's going to include one of these lower probabilities, 2 of these lower probabilities. Okay, so this right here, let's just kind of decompose it a little bit. This is a discrete probability function, right? It's finite, right? I have only 6 faces. They each have a probability, okay? Each probability, 1/4 or 1/8, right? Each probability individually is between 0 and 1, okay? If I were to add up 1/4 plus 1/4 plus 1/8, plus 1/8, plus 1/8, plus 1/8. It's going to sum up to 1. Okay, so we have a valid probability mass function that we're doing here. It's always good. You will be asked specifically, is this a valid function or not? So just make sure that you know how to do it. But in real life, you'll probably just want to check to make sure that things are set up correctly or that they're valid, that you're looking at it. Okay, so back to the question at hand. What's the probability that an even number is going to show up on a given roll of the die? So we're going to say, let's just enumerate, our even numbers are equal to 2, 4, and 6. Okay, so that means that probability that our random variable x is an even number, okay, is the probability that x is equal to 2 plus the probability that x is equal to 4 plus the probability that x is equal to 6. Okay. Now I go back to where I was assigned these probabilities and I fill in the blank. So the probability that x is equal to 2 is 1/8. X is equal to 4 is 1/8. And then x is equal to 6 is 1/4. Okay. I'm just going to sum all these up and I'm going to get 1/2. So it's still equal to 1/2. Okay, but we had to break it down. First, it was always a good check to see if it was a valid PDF, valid PMF to begin with. Okay, so I can leave that up on the screen a little bit here too. So example 2, we've got this variable x, a random variable. It can take on the values 1, 2, 3, or 4. So the probabilities associated with each outcome are here. When x is equal to 1, it's a probability of 0.1. When x is equal to 2, 0.3. X is equal to 3.4, x is equal to 4.2. Okay, this right here, this table, is our probability mass function, okay? Because it tells us on our given outcomes what's the probability of each, okay? So I'm just going to take a look. 0.1 plus 0.3 plus 0.4 plus 0.2, this is all going to sum up to 1, which is a good check, right? So we wanted to make sure that our probability sum to 1. Each individual probability is between 0 and 1, so far we're fulfilling our definition for a valid probability mass function. Okay, so part A, B, and C, we want to know different things. What's the probability that x is equal to 2 or x is equal to 3? X is equal to 2 or probability that x is equal to 3. So I'm just going to sum these up, right? So I would say probability of x equals 2 plus the probability of x equals 3. Okay, and I look in my table. X is equal to 2 is 0.3. Probability x is equal to 3 is 0.4. So my total probability, excuse me, that it's equal to 2 or 3 is equal to 0.7. Right? I just summed up these two individual probabilities. So we want to find what's the probability that part B says, probability that x is greater than 1. We'd write it like this. Okay, so if x is greater than 1, okay, that means I've got 2, 3, or 4, okay? So I can say this is going to equal to 1 minus the probability that x is equal to 1. Okay, I mean, these are small, set of numbers, so it's not so bad. We want to give an example of, complementary math here. So this is going to be 1 minus, right? X is equal to 1 minus 0.1, which is equal to 0.9, okay? Which is what I would get if I summed up 2, 3, or 4. But just to show you an alternate method for doing our complementary rule. Okay, so we use the complementary rule for that. Okay. Probability histogram is a really great way to actually graph out your probability mass function. We'll do this also for probability density functions or continuous random variables. This is often how you're going to be taking a look at things, but let's go ahead and draw it out. So what I have on my axis, on my x-axis, are the outcomes. I'm sorry, can't see that. Outcomes. So I've got 1, 2, 3, 4. Okay, and on my y-axis are my associated probabilities. So here's 0.1, 0.2, 0.3, 0.4. Okay, so based on the table that we had at the beginning that we were given, right, when I have my outcome equal to 1, my probability is equal to 0.1. Okay, when my outcome is equal to 2, my probability is equal to 0.3. When my outcome is equal to 3, I'm looking at my table, is equal to 0.4. When my outcome is equal to 4, I'm looking at 0.2. Okay, so this is our probability histogram. Okay, if I were to add up the areas of each of these rectangles, right, this is 0.1, 0.2, 0.1, 0.3, 0.4, 0.2, it's the whole area under here is going to sum up to equal to 1. Okay, that's something that when we get to our continuous, it's not going to be like a block, it's going to be a continuous function. Okay, so we're going to think about how we're going to add up the area under our curve, okay, to know what's our total probability value. So this is our probability mass function right here, okay, is a way of turning into a graph our probability mass function, okay, that we had in the table. I'll give you guys a second to finish writing that down. Okay. All right. I'm going to move on to the next question, next example, which says, example 3, since we have a, oh, sorry, let me put this here. A fair coin is tossed until a head comes up the first time. What are the chances of that happening on an odd numbered toss? Okay, so this is our sample space is potentially infinite, right? I mean, I mean, in reality, this is a fair coin, so I have a 50-50 chance of getting a head or a tail. But, you know, conceivably, I could be tossing this coin forever and never actually get a head on here, okay? So we call this accountably infinite. It's infinite because what we just described, and countably because, as we're going to see, and as we have seen before too in previous chapters, that I can come up with an algorithm to describe, right, how many heads I'm getting or how many tails I'm getting. Okay, so let's just kind of, I'm going to start enumerating a little bit so I can kind of see what the pattern looks like. So I'm looking for a head on the first toss. So I could get a head on the first toss. This is, let's write toss number. So this is my first toss right there. So I could get a tail on the first toss and then a head on the second toss. Okay, I could get a tail, and then a head. Right, so this is my third toss here. I could get a tail, and then a head. Right, so I have to toss it 3 times before I finally get a head. And then I can get a tail, and then a head. This is my 5th toss. I'm writing down only the odd numbered tosses, right, because that was what we were asked to look for. And this goes and so on and so forth. So that's why it's infinite, because we could toss this coin forever before we finally get the head. Okay, but I want to look at what's our probability that I'm going to get that head on the odd numbered toss. So I need to come up with a pattern to be able to describe this. Because let's think about some of the stuff that we've done before. It's a fair coin. And I have 2 possibilities, a head or a tail. So that means my probability of a head is 1/2. And a probability of a tail is also 1/2. Okay. And K, I'll call K, which is the toss number that we're working with, right? So the toss number, right, could be 1, 2, 3, 4, 5, whatever. Okay. So my toss number. So let's write out, instead of heads and tails, I'm going to write out their probabilities. So probability of a head is 1/2, and this is on our first toss. Then the probability of a tail is 1/2, then the probability of a head is 1/2. Probability of a tail, and then a head, tail, and then a head, and so on and so forth. Okay, it's a fair coin, so you don't necessarily see that it's a head or a tail when we do this out, but I have to take into account both probabilities here. Okay, so this is equal to 1/2 to the 1, 1/2 to the 2. I'm trying to build up a pattern, right? So that's a 2. Sorry, this is 1/2 to the 3, 1/2. Oops, sorry, 1/2 to the 4, 1, 2, 3, 4, and so on and so forth. So I'm going to have also 1/2 to the 5, 1/2 to the 6, 1/2 to the 7, and so on and so forth. Okay, so K is my toss number, right, which is equal to 1, 2, 3, 4, 5, so on and so forth, right? So I can say I'm on my first toss, right? I'm on my second toss, third toss. Well, that's my toss number, so I can write this out as, right, 1/2 to the k is going to give me, like, which particular toss number am I talking about? Okay, so, but in reality, we were told the nature of this thing is we only want the odd numbers, right? That was the nature of the problem that we were looking at, only the odd numbers. So I'm going to say the probability that my random variable x is equal to an odd number, right? That's what I'm looking for, which means I'm going to sum up the probability that x is equal to 1, probability that x is equal to 3, probability that x is equal to 5, and so on and so forth, 7, 9, whatever. Okay, so I'm going to, this is going to be 1/2 to the 1, half to the 3, it's a 3, 1/2 to the 5, 1/2 to the 7th, 1/2 to the 9th, so on and so forth. I'm summing up all these probabilities. Okay, so I'm going to think about this. So this is actually, let's sum these up. So k starts at 0, and it can go on forever, right? This is an infinite setup here. So this is going to be 1/2. We only want the odd numbers. So I'm going to say 2k plus 1. 2k plus 1 says I'm only looking for the odd numbers. Let's just check to make sure that we have this formula right. When k equals 0, 2 times 0 plus 1, it gives me 1. When k equals 1, right, 2 times 1 plus 1 is 3. Okay, so it looks like we've got the right formula here. It's always a good idea to check that. So this, I need to actually break this down into something a little bit more formulaic. So let's just think about offline here. This is our scrap word. So I'm going to say 1/2 raised to the 2k plus 1 power. What does that look like? Okay, so 1/2 raised to the 2k plus 1 power is like saying I've got 1/2 to the 2k times 1/2 to the 1, right? Remember your exponents law, same base, right? If I've got the same base, I can add the exponents, which is what we did, okay? My exponent law says I can do something with this 1/2 to the 2k. So this is like saying 1/2 squared raised to the k power, okay? Remember, because our law of exponents says I can multiply these together, and this is times 1/2 to the 1. So 1/2 squared is 1/4 raised to the k power times 1/2. Okay, so this, oops, sorry, I don't know if you can see that. So this bit right here is what I'm going to substitute back in up here, what that's going to equal to. So this is going to equal to k equals 0 to infinity. This is going to be 1/2 times 1/4 to the k. Okay, I broke it down. This looks like a series, right? I'm going to sum up all this stuff. This right here we recognize, right, as a geometric series, okay, which means I can do stuff with. I can sum it up, right? I can sum it up because my R value satisfies the criteria for the geometric series converging, because R is between 0 and 1. Our absolute value of R is between 0 and 1, which means now I can figure out what the sum is. Sum is going to equal to A over 1 minus R, okay, which is our A value is equal to 1/2, 1 minus 1/4, okay? So this is going to sum all up. I'll do some math. This is going to sum up to be equal to 2/3, okay, which is going to tell us that's the probability, okay? It answers our question. What's the probability that the first head, right, is going to happen on an odd numbered toss, okay, 2/3. But we needed to come up with, we call it countably infinite, because we needed to come up with a formula for being able to describe that, okay? And our geometric series is a way to do that here. Okay, I'll do one more example today, and then we'll break for this, and then we'll come up and we'll talk tomorrow. We'll finish up chapter 3.3. Make sure you guys, I'll give you guys another second to finish writing that. This is kind of like, in a sense, it's similar to the quiz problem that we had where we had a geometric series that we needed to analyze. Okay. Countably infinite is nice because I can come up with a formula to describe it. And actually, geometric series are nice because if they converge, I can calculate a sum, which then becomes the probability that I'm looking for. Okay. So example 4. All right. Example 4 says, excuse me, if we're tossing 2 fair dice, okay, I equals the face of die 1, okay, J equals the face of die 2, right? We're going to assume that this is a 6-sided die, right? So I could be 1, 2, 3, 4, 5, 6. J could be 1, 2, 3, 4, 5, 6. Okay. And then capital X is the random variable for their sum. So I've got two pair die. I roll them. I take a look at their faces, and I add the two face values, and I'm going to get X, which is their sum. Okay. So we want to know a bunch of things. So what's the sample space for our whole setup here, which is what we did, right? Remember we were talking about this last week. If k equals a particular value of this sum, what's the probability that x equals k? And we want to draw a probability density function for this. Okay, let's go ahead and kind of write down what we know, and then we'll start working our way through the problem. Okay, so that means let's start. X is our random variable. So I've got I and j on here. This is the I comma j, right? And this is going to equal to I plus j. Okay, that's the sum. These are the individual faces in there. So we want to, I'm going to generalize this, right? And I'll say x1 equals the result of die 1. Okay, I roll the first die, I get x sub 1. Okay, yeah, here, my random variable x. Random variable x2 is our result of die 2. Okay, now my random variable, my big random variable x, is equal to the sum of the face values on here. Okay, what I've just done in generalizing it is I've opened it up to being able to do more than 2 die. I can roll 3 pair die, 4 pair die, whatever, and I can just say x is equal to the sum of their faces, right? By assigning these sub values, okay, for the results, and then I can assign it to a big random variable, which is the sum. Okay, so now let's talk about our sample space, our big S sample space. So this is going to be I and j, given that I can equal 1, 2, 3, 4, 5, and 6. These are the possible values for I. And our j can equal to 1, 2, 3, 4, 5, and 6. Okay, they're both 6-sided die. Okay, then that means I've got 6 possible outcomes for die 1, 6 possible outcomes for die 2. Okay, so we have 6 times 6, 36 possibilities. Okay, that would be the table that we created last week, right? Where I had die 2 and die 1, right? And I had all those ordered pairs, 36 of them, right? For all the different possible combinations. I get a 1 on die 1 and a 1 on die 2, a 1 on die 1 and a 2 on die 2, and so on and so forth for all those different 36 possibilities. Okay, so now the sum, okay, for the sample space, this is going to be I plus j, right? I take that big table that we came up with last week with all those possible outcomes for each of the die. I'm going to add them, right? So 1 plus 1 is equal to 2. 1 plus 2 is equal to 3, because that's going to satisfy a random variable. That's the question. You always want to keep in your mind, what's the random variable that's being asked? So to sum these up, right, I could have a 2, or I could have a 3, or a 4, or 5. These are the sums now of the two faces of each die. 6, 7, 8, 9, 10, 11, and a 12. My minimum, 2 comes from when I sum 1 on die 1 and 1 on die 2. My maximum comes from when I get a 6 on die 1 and a 6 on die 2. Okay, so these are our sums of the two die faces, right? That's what this is. So this is our sample space that we're working with. Because our random variable, we were told at the beginning, was for the sum of those two faces. Okay, so that's our sample space here. Okay, that answers, so this is our part A. Okay, so part B says, if k is a particular instance of this sum, what's the probability that x equals k? They don't tell me what x is going to equal specifically, so I have to assume I'm going to build up a table for all these possible values. Okay, so I'm going to start, let's do this. I'm going to build up a table. So I'm going to say my k value, what it could be, probability that x is equal to k. So this is probability that x is equal to a particular value of k. Okay, so my k could be 2. Okay, I have, the only possibilities that I have would be 1 and 1 that are going to sum up to be equal to 2. So I get a 1 out of 36. That's the probability that the sum is going to be equal to 2. I have only one possible outcome for that. My k, my sum could be equal to 3. The sum up to 3, I have 1 and a 2, and a 2 and a 1. I'm writing down what the possibilities are so you can see where these probability numbers are coming from. So I have 2 out of 36 that are going to generate a sum equal to 3. For a sum equal to 4, I can get a 2 and a 2. I can get a 1 and a 3, and a 3 and a 1. Okay, which means I have 3 possibilities out of 36. See, my k values come from here, okay, and then my probabilities here are going to come from that overall like grid that we came up with. I'm going to count up all of those instances, right, that are going to make this sum possible. Okay, let's keep going. I'll build this up for the whole bit. So if my sum is going to equal to 5, the ways I can get that are 2 and 3, 3 and 2, 4 and 1, and 1 and 4. Okay, so I have now 4 possibilities out of 36 to generate a sum of 5. To generate a sum of 6, I can get 3 and 3, 4 and 2, 5 and 1. I can do 1 and 5, and 2 and 4. So 1, 2, 3, 4, 5. So I have 5 out of 36 possible ways of generating a sum of 6. For a sum of 7, I'm going to do this too. I'll enumerate these out just so you can see. You get a 1 and a 6, a 2 and a 5, a 3 and a 4, a 4 and a 3, 5 and a 2, and a 6 and a 1. I'm going through that table. 1, 2, 3, 4, 5, 6. I have 6 out of 36. Okay. Do this again for 8. I'm enumerating this because I think, I'm trying to remember, you may have to do this for like a homework problem, but it helps to kind of visualize, you know, where this is coming from. 8. So to sum up to 8, I've got 2 and a 6. I've got a 3 and a 5. I have 4 and 4. I have 5 and a 3, and a 6 and a 2. So 1, 2, 3, 4, 5. 5 out of 36. Okay. Sum up to 9. We're going to do the same thing. So for this one, I can get a 3 and a 6. I can get 4 and a 5. I can get a 5 and a 4, and a 6 and a 3. Okay, so I've got 4 out of 36 as a probability for 9. I'm going to continue this table off to the side here. So this is, okay. Here, I ran out of space, so I'm going to do it off to the side. So to get a sum of 10, okay. To sum up to 10, I have to use 5 and 5, 6 and 4, and 4 and 6, right? So I have 3 out of 36 will give me a probability for summing up to 10. To sum up to 11, I can get 5 and 6, and 6 and 5, which is only 2 out of 36. And to sum up to 12, right, you can imagine you can only use 6 and 6, which is 1 out of 36. Let's see if you can see this, almost the whole table here. Can't get the whole thing quite. I'm missing a little bit down at the bottom. Okay, so this maps out, okay, our probability for any particular k value, okay, my x is going to equal to, what's the probability that the sum is going to equal to? It's 1 out of 36. What's the probability that x is equal to 5, that the sum is equal to 5? It's 4 out of 36. Okay, when I look at this table, we're going to draw that histogram that we showed before. We're going to draw a graph. When I look at this table, I can see that my highest probability is summing up to 7. I have the most combinations that are going to sum up to 7. It's probably why, remember last week we did those homework problems with the game of craps, and 7 was, you can either win right away or you could lose with a point of 7. Well, you can see, right, 7 is one of those numbers. When you sum up to 7, you have the most possibilities that are going to sum up to 7. So it kind of makes sense that you would have a game of chance where it's a little bit biased against you, because if 7 is a losing point, right, then that's the one that's going to happen the most, potentially, where its probability is the highest. Okay, so I'm going to take this and I'm going to draw a graph, what we call our probability mass function or a probability density function. Oh, looks like I ran out of space. Okay, I'm switching to a blank page here to finish this. I should have given you more room for these here. Sometimes I print these off single-sided so I can just keep them all in one. So this is example 4. Okay, so we want to be able to graph or plot the probability. We're calling it probability density function. It's also a mass function. Okay, so just like what we did before with our x and y axis, right? My x-axis is the possible outcome that I can have. So I can have a sum of 2, I can have a sum of 3, a sum of 4, a sum of 5, a sum of 6, 7, 8, 9, 10, 11, or 12. These are my outcomes, right? Or my random variable x could equal, my sum could equal 2 through 12. Now on my y-axis, these are my individual probabilities. So I'm going to go up to 1 out of 36. This is a 0. 1 out of 36. 2, 3, 4, 5, and 6. 2 out of 36. 3 out of 36. 4 out of 36. 5 out of 36. 6 out of 36. So these are our probabilities, okay, for each individual outcome. Okay, and I'm going to graph it out based on that table that we just created, right? So for an outcome of 2, I have a 1 out of 36. For my outcome of 3, I have a 2 out of 36. For 4, I have 3. For 5, I have a 4 out of 36. Let me get this graph right. For 6, we have a 5. And for 7, we have our highest at 6. And then 8, we start to come back down. There's a symmetry here. Okay, and then 9. And then 10 is 3. 11 is 2. And then 12 is 1. Let me draw this out. All I did was I looked at our table, right? You can see. So when our outcome is equal to 2, our probability is equal to 1 out of 36. That's where these numbers came from to give me my graph, my probability mass function, my discrete variable. This, by the way, we're going to see this a lot. This kind of a curve, right? It's called our norm. It's the basis for our normal distribution curve, right? It's this bell-shaped curve. Okay, it's really nice when we see this nice and symmetric like this. It kind of helps us. We're going to do a lot of statistics on graphs that look like this, but that's coming for the second half of the class. Okay, so that's our probability density or mass function. So let's just talk really quick. I just want to do a quick example. So if I say the probability that x is equal to 5, say for example, where I would say the probability x, I could write it like this, okay? Which is also, these are just different ways of writing it. So if you see it, s is an element of s, given that x of s equals 5. This is using all the different notation types for how we do it. Most often, we're going to see it in these two. Okay, this is how our book does it. This is how we're predominantly going to do it in the class. So this is equal to the probability of, if I have 1 and a 4, 4 and a 1. These are our combinations, 2 and 3, 3 and 2, right? But I can also read my graph. This is 4 out of 36. So this is a 1 out of 36. This is a 1 out of 36, 36, 36, which gives me an overall probability of 4 out of 36, right? I can also look at my graph, like I say, probability that x is equal to 5 is equal to 4 out of 36. Or I could look at my table, right? In my table, it said the probability that x was equal to 5 is equal to 4 out of 36, okay? So these are using different methods, right? We're tabulating it, we're graphing it, and this is kind of like the old method that we did before, which is we're going to add up these individual probabilities for how we're going to get to this. Oh, they say 34. Right, this is a 36. Okay. To give us the overall probability that x is going to equal to 5. Right. Now, likewise, if we say, just as a quick example, that x is less than 5, okay, which is the same way as saying the probability that x can equal to 2, x can equal to 3, or x can equal to 4. Now, it says less than 5, right? So I'm not summing up also 5 because I don't have an inclusive on here. So I'm going to look at my table, I'm going to look at my graph, and I'm going to find out what's the probability that x is equal to 2. That's 1 out of 36. Probability that x is equal to 3, that's equal to 2 out of 36. And x is equal to 4 is 3 out of 36. I'm going to sum all these up, and I'm going to get 6 out of 36, which is just 1/6. Okay. So these are the types of questions that you would see, right? Like on your homework or other examples that you would do, okay? And we can get this information here from the table that we created, right? Or we can get it from the graph that we created. The graph comes from the table, from all those individual calculations that we do, okay? I'm going to stop here today, and then tomorrow we'll pick up with a couple concepts about taking this whole table here and doing a running sum on this whole table. We'll take this example. We'll do a running sum on this whole table, and we'll come up with what we call a cumulative distribution function. Okay, we're going to need that as well. And then we'll work through one whole example that's similar to a homework problem that you would need to do in chapter 3.3. We'll do that tomorrow. Okay. Anyway, that's the end of chapter 3.3. And I'll scan these in and I'll give them to you. And then when I have the rest of 3.3, I'll put those up on our Blackboard page. Okay. I have office hours today if you guys want to come by and ask questions about stuff. If you want to ask about the homeworks or if you want to ask about test reviews, that's fine. Otherwise, have a great day, and I'll talk to you guys later.